Hi, I'm Dongdong Chen, and in this video, I will talk about our new paper Robust Equivariant Imaging, a fully unsupervised framework for learning to image from noise and partial measurements. This is a joint work with Julián Tachella and Davies. In this paper, we tackle the imaging inverse problems. Let me first go over the specific formulation we are gonna consider. Here we are interested in a unknown image X that's presented through an instrument or sensing operator A, which can be linear or nonlinear. But beyond the sensing operator, there is also some noise that comes in through sensing, and we are gonna end up observing the measurement data Y. The mapping from unknown X to Y is called as forward process, which is pretty straightforward to do. As long as you know the physics of the sensing operator A and you know the statistics of noise. Now what we're really interested in are the inverse problems, and this is a practical problem of trying to recover the unknown X, the true object, given the measurement Y. Inverse problems are ubiquitous in science and engineering. Many problems in scientific imaging and beyond can be formulated as inverse problems. Here is a table with some applications. What we care about is recovering X from Y. For example, we want to recover our brain images from the case-based measurement that generated by MR scanner. We want to recover the black hole image from its spatial frequency data that collected by telescopes. We also want to recover the structure of coronaviruses from its 2D projections that generated by cryo-AM. We already know that the state-of-the-art techniques can solve many inverse problems using advanced neural networks, using supervised learning on X and Y pairs. But the problem is the training samples may be expensive or impossible to get, which is very often in biomedical imaging or astronomical imaging. This raises the chicken and egg problem. So I need my X to learn F, but I need my F to reconstruct X. To avoid this, an equivariant imaging framework was proposed to direct learn F from Y alone. The motivation of EI is very simple. We know that the single-node set usually enjoys specific invariance. For example, the lateral images set is shift or rotation invariant, while the CT or MR images set is rotation invariant. Under this prior, we find the four imaging systems is equivariant, which can be used to learn F without Groundtruth. EI learns F by minimizing the sum of measurement consistency and the error from equivariance constraint. After some training epochs, EI can learn out the function F, which can be used to reconstruct new tested measurements data. It was noting in EI, the function F can be implemented by any advanced neural networks, such as UNet, ResNet, transformers, or on-road architectures. However, as can be seen, we found the performance of EI degrades with the measurement noise. In this paper, we proposed a robust extension to EI to solve this limitation. The main idea is to exploit Stein's unbiased risk estimator to handle the noise and learning the image model with equivariance constraint. Please check our paper for the detailed formulation of our Schur losses. We compared the robust EI with EI and supervised learning on different inverse problems. Robust EI achieved considerable performance gains and approaching the quality of reconstruction trained with Groundtruth data using supervised learning. In this paper, we introduced a lower fully unsupervised learning framework that can learn the reconstruction function from the measurements data alone. The code has been released. Please have a try. If you have any questions, please come to my poster and talk to me. Thanks for your attention.